the Earth's magnetic field. It's what makes our compasses point north. But it does a lot more. It helps to keep the Earth a living planet. Our neighbors, Venus and Mars, have only weak magnetic fields, which means they're unprotected from the deadly radiation sweeping through the solar system. The Earth, on the other hand, exists within a vast magnetic cocoon. A force field that for billions of years has sheltered us on our journey through space.
With lightning, it's almost embarrassing. We've been studying lightning since the time of Franklin, and for over 200 years, we still haven't answered the big questions. How does lightning work? How does it get started up in the thunderstorms? How does it propagate for miles through the air from way up there where it's initiated down to our feet?
Lightning is static electricity, and you can make it yourself at home.
Let me take my shoes off, and when I do, I'm going to rub my feet on the carpet. As I rub my feet, friction is going to separate electrical charge. Positive charge is going one way, negative charge the other. Now when charges separate, they want to get back together. A large electric field can build up, and when this happens, you can get a spark. We think that something like that is going on inside a thundercloud when it makes lightning.
To send a current across this tiny distance takes up to 25,000 volts. But lightning bolts can be almost 200 kilometers long. Sending a current through this much air takes millions of volts, a massive electrical charge that so far scientists have failed to find.
You have to ask, well, where is the finger that's concentrating the charge to making the big fields to produce the spark? And we're having a really hard time figuring out what that finger is.
Fire!
It trails a copper wire that acts like a lightning conductor. Millions of volts of electricity race from the cloud to the ground. Dwyer uses data from this experiment to investigate how lightning can pass through several kilometers of air, and he looks for the answer in outer space. In a galaxy far away, a star explodes. Millions of microscopic electrically charged particles are forced out into space. These are known as cosmic rays. Traveling at nearly the speed of light, they race across millions of kilometers, taking millions of light years to reach Earth. Dwyer wondered if cosmic rays could explain how electricity travels through several kilometers of air. Billions of these rays bombard our planet every second. They're invisible and inaudible. But when a cosmic ray travels through the atmosphere, it momentarily rips apart the air's molecular structure. This produces X-rays, electromagnetic waves of radiation which can be measured. Could cosmic rays be the missing link in the story of lightning? It sounds like science fiction. Even the optimistic Dwyer thinks it's a long shot.
When we got our first triggered lightning and made our first X-ray measurements, I didn't even get around to looking at the data for a couple weeks, because I wasn't really expecting to see anything. When I sat down finally, there on the screen was an X-ray pulse right when the lightning occurred. I thought, well, what's the chance of that happening? I mean, right there at the same time. So we looked at the next stroke, and there was another pulse, even bigger. We looked at the next stroke, another pulse, and another pulse with the next stroke. Every time we looked, we saw a big burst of X-rays hitting our instrument at the exact time that lightning struck.
Dwyer believes this is a clue that something has changed the air's atomic structure. And he thinks that something could be cosmic rays.
For centuries, we've been laboring under the assumption that lightning is just a normal kind of discharge, like the finger touching the doorknob. We suddenly see now that this was wrong.
If Dwyer's right, when a cosmic ray hits a cloud, it causes a huge momentary surge in electricity, enough to create a spark, but too brief to be measured. The ray then hurtles on towards the ground. The superfast moving particles collide with air molecules and rip them apart. For a fraction of a second, the air becomes electrically conductive and provides a path down which the current can run. Now lightning can strike. A channel of negative electrical charge shoots from the bottom of a cloud. It heads towards the ground in rapid steps, each taking just 50 millionths of a second. The evidence pointed to the sun. But in 2004, Green took a chance look at a magazine, and everything changed. An article on the distribution of lightning captured his attention.
The beautiful maps of lightning changed my concept of where lightning was actually being generated, drew my attention to the article immediately.
Green noticed that lightning exhibits exactly the same characteristics as the clearance of the safe slot. It occurs more over land than sea, more during the day than night, and more in the summer than the winter.
That was the time that we then knew that this had to be related to phenomena that was occurring on the Earth. And the only thing, of course, that we know enters into space is lightning.
But how could lightning on Earth affect the safe slot 6,500 kilometers up? When a lightning bolt tears through the air, it doesn't just produce light and sound, it also creates radio waves. If you turn on your radio when there's a storm nearby, you can hear them as interference. But if you tune in with an all-frequencies receiver, you can pick up more than just crackle. This eerie whistling is the sound of those radio waves after they've traveled through space.
What we've been listening to are lightning spherics. And these are emissions that occur from lightning hundreds of miles away that are propagated to us and are received in our antennas.
Green realized that these radio waves were the missing link. They connected lightning on Earth with the safe slot in space.
We never realized the importance that the ground is having on space.
In 2005, Jim and his team came up with a radical new theory. Less than a second after a lightning strike on Earth, the radio wave reaches the radiation belts. There, it interacts with the electrically charged particles, the radiation. It forces the particles out of the safe slot. The radiation is cleared, and the safe slot returns to normal.
We always had thought about lightning in the past, I believe, as a destructive mechanism. But I think we're discovering many of its beneficial factors.
If Green is right, without lightning, radiation would soon fill the safe slot. Satellites would fail, taking out many things we've come to rely on. Global communications, navigation systems, cell phones, and satellite television could all shut down. Life as we know it would grind to a halt.
If lightning stopped tomorrow, we would see a dramatic change in the way we live today. It's probably one of those fundamental parts of the equation that really contribute to life on Earth.
For millions of years, lightning has formed a part of our darkest visions and most terrifying myths. But now we're closer than ever to unlocking its secrets, and the more we discover, the more lightning defies expectation. Its origins may lie far beyond our world. It can take strange forms and create dazzling light shows. It is devastating, beautiful, and essential to life as we know it. The incredible journey of a lightning bolt takes us from outer space.
It seems the Earth's magnetic